Hello everyone, thank you for joining this webinar. My name is Lino Capponi and I'm an applications engineer here at Plexim. I'm excited to present you today's webinar on microgrid and distributed energy resource projects using PLECS and the PLECS Rtbox. One emphasis of this webinar is going to be on the value of real-time simulation to accelerate the development and also the deployment of microgrid projects. During the presentation, I might use a few terms interchangeably. So when I say offline or desktop simulation, it means that the simulation model is truly running here on my personal computer, whereas online, real-time or hardware in the loop will indicate that the model is executed in real-time on the PLECS Rtbox as well as here on the embedded microcontrollers. So here's the agenda for today's webinar. First of all, I will give a brief introduction to Plexim, the company, and then we will directly start with our main topic of today's presentation, so DC microgrids. First, I will just give you I will introduce a few microgrid basics in order to have a common language, and I will tell you something about the challenge of simulating such systems. Then we will directly have a look in a simulation model running in PLECS standalone. And after a short introduction to the PLECS coder and the PLECS Rtbox, we will make the transition between the offline simulation towards a real-time simulation running on the setup that you see here on my desk. And actually, before moving forward to the next slide, I just want to introduce quickly here the setup that you see on my desk. So you see that we have here two Rtboxes, one Rtbox 3, one Rtbox 1. They are interconnected together, and we have here three different microcontrollers that we will use for the real-time simulation of our DC microgrid model. So for those of you who are unfamiliar with us, here a short introduction who we are. So we, Plexim, develop a design toolchain for power electronic systems. So not only for the designing, but also for the testing. Since almost 20 years, we sell our simulation software PLECS that is available in two different versions. PLECS Blockset that is fully integrated in the MathWorks Simulink environment, and PLECS Standalone, which is an independent software package. Since 2016, we have also our own real-time simulation platform called the PLECS Rtbox that you see here on my desk. Since almost 2 years, we offer also tools for the automatic code generation for different embedded targets. So for example, here the C2000 family from Texas Instruments, as well as here microcontrollers from the G4 series from STM32. During this presentation, you will see a few different tools. So first of all, I will show you PLECS Standalone, where we will analyze the DC microgrid offline simulation model. Then I will use the PLECS coder in order to make the transition between the offline simulation towards a real-time simulation. You will see for sure then also the PLECS Rtbox and our code generation tool for embedded targets. So let's start with our main topic, DC microgrids. So here on this slide, I just want to introduce some key microgrid concepts in order to have a common language. So for me, a microgrid in general is a collection of different sources and loads and storage systems to a common feeder. In a DC microgrid, this common feeder is based on DC technology. So actually here on the right side, you see a basic schematic of a microgrid. So as I said, you have then here different systems or energy storage systems that are connected here to this common DC link feeder. You have a producer and some loads that are connected together. Here we have then the interface between our DC microgrid to the mains utility grid. And as you can see, this is also done by using a power electronic converter system. So this results then in having a controlled power flow between our DC microgrid and the mains utility grid. This conversion stage in between the two different grids will then also, let's say, dynamically decouple our DC microgrid from the mains utility grid. Depending on the control of the microgrid, it can operate both in grid connected and in off-grid, so in islanded operation mode, or can even switch in between the two operation modes seamlessly. When we are disconnected from our mains utility grid, that also means that we have to feed all our loads or to absorb the excess of power from our producers locally with some kind of storage systems. We then also have to make sure that we have stable operation without having the possibility to exchange the excess of power, for example, with the mains. As I said here, the power excess in our microgrid can be exchanged in a controlled way with the mains utility grid. And in the end, this offers then to have a very grid-friendly way to integrate quite a huge amount of renewable energy sources to the mains utility grid without reducing, let's say, the stability of the mains utility grid due to fast power variations, for example. So we can then solve the problems related to renewable energy sources locally by using storage systems, by consuming locally, and we can then exchange the excess of production in a controlled way with the mains. Also, in terms of reliability, there are some advantages of microgrids. First of all, we can operate, or we can seamlessly change the operation mode between grid connected and off-grid operation mode. And then usually we have not only one system that is responsible to have a safe and reliable operation of our DC link, but we have several systems that work in parallel to achieve this goal. So in terms of reliability, we don't have a single point of failure in such a system. Regarding economics and also efficiency, there are some advantages of a DC microgrid compared to an AC system. For example, here, several loads and also sources are based, by nature, are based on DC technology. So for example, here the PV production can be interfaced and just with a DC-DC converter to our DC link, and here for a variable speed drive, usually what we have if we want to connect such a system to an AC grid, we have a double conversion converter. So we have an AC to DC, then a DC to AC conversion stage. And if we connect our variable speed drive directly to a system that is based on DC, we can omit this first conversion stage and increase the efficiency of our system. And for sure, in the same time, also reduce the costs. So there are quite few arguments for a microgrid based on DC technology or for microgrids in general. As you have seen before, a microgrid is an interconnection of different systems to an even larger system. This makes a microgrid quite complex. So we have then quite a big variety of different time constants that appear in this bigger system. So there are very small time constants related to the switching operation of the power electronic converters, so in the nano to microsecond time range. Some intermediate time constants related to voltage and current control loops and so on. And then on the very other end, on the slow end, we have very slow time constants related to probably a supervisory controller that tries to optimize the power flow between the different sources and loads, a charge cycle on a storage system, and this huge difference between the slowest and fastest time constants makes it really hard to simulate such system, then especially in real time. Because there we have to make sure that our simulation model, our real-time simulation model, that will then later be executed here on the Rtbox, has enough fidelity to capture also the effects that happen here on the fast end. So how can you use PLECS for your microgrid research and development? Basically, there are two key ways to do so. First of all, there is offline simulation, which is quite a traditional way to analyze such systems. So you build a simulation model of your hardware and also a simulation model of your controls, for example in PLECS standalone, and you can then simulate different scenarios. Then there is hardware in the loop simulation, and there we emulate the physical behavior of your plant by running a simulation model in real time on a real-time simulator. So the real-time simulator, it will then emulate the behavior of the plant system, and all the measurements, the current and voltage measurements, are converted into real physical signals that are made then accessible here in the front panel of the Rtbox. There we can then connect our system under test, which is usually then a microcontroller, for example. And the microcontroller will run then its control code also in real time, and we can test this control approach then in a safe environment first without having the need to have even a prototype available and to build our system. So let's go now towards the offline simulation of our DC microgrid model. So as I said before, here on the right side, you can see actually the case study that we will use for first the offline simulation and then the real-time simulation. So we have two battery storage systems that are connected by means of DC-DC converters to our common DC link feeder. We have a producer and a consumer. And then for sure we have also this interface or this interlinking converter between our DC microgrid towards the mains utility grid. To have a safe and stable and reliable operation of our DC link or of our DC microgrid, we need at least one conversion system that controls the DC link voltage. Usually, in a DC microgrid, you don't have a single system that does this, but you have several systems that operate in parallel. And also here in our case study, we use a parallel operation of several systems that control this DC link voltage. And in our case, the two battery storage systems control the DC bus voltage close to the reference value. So we have here parallel operation of those two systems. If you have parallel operation, you have to ensure the load sharing among the two systems or among the different systems. And this is achieved in our case study just by using a simple droop controller that is implemented here locally in each control loop of this energy storage system. All other conversion systems, so the grid interface converter, the producer and the load, are operated in current controlled mode. So let's open now PLECS standalone and let's see how this model is implemented there. So I open now our DC microgrid model in order to analyze it here during an offline simulation. For the moment, I will not focus too much what's happening here on the root schematic level. I will explain then why everything is regrouped in different subsystems in the second half of the presentation, where we focus then on the real-time simulation of this system. So for the moment here, just focus what's happening here in this subsystem there. Here you see the basic structure of the DC microgrid. So we have here the PV production, a generic load that acts as a constant power load to the microgrid. Here we have the two battery storage systems and the grid interlinking converter between the DC microgrid towards the mains utility grid. So let's have a look how the different converters are implemented. So we start here first with the battery storage system. You can see here the topology that we use. So here on the very right side we have a battery model and then two dual active bridges. On the input side they are connected in parallel, and here on the output side or on the DC link side they are connected in series. You can also see that this is a fully switched model, so each power electronic semiconductor receives a gate signal. So this is the topology that we use for the two battery storage systems. Then we have here our grid interlinking converter, also there. Let's see how this model is implemented. This coupling circuit will be explained in the second half of the presentation. And here we have then the topology that we use. So you can see it's a three-level voltage source inverter that is connected here, our filter inductor, to the mains utility grid. Also here, this is a fully switched model, so each IGBT receives a gate signal. For the PV production and here the constant power load, the implementation is a little bit different. Because here in this simulation model, or for this simulation scenario, we just use them to create some power variation, some load flow in our DC microgrid. So because here we are focusing, let's say, more on the voltage control of our DC link and in order to test the implementation of this control approach. So here for the constant power load, you can see it's not a switched model, it's just a behavioral model. So let's start now the simulation. And during the simulation run, I will explain you how the controls of those three inverters is implemented. For this, I go back to the root schematic level. And here you can see the controls or the controller models for the grid interface converter and the two battery storage systems. The controls for the battery storage systems is identical because we have the same topology, the same control goal, and therefore also the same control algorithm. So here you see then actually how this model is, or how this controller is implemented. First of all, you can identify here a few different special blocks with this small annotation TI. And in fact, those are target-specific blocks. What this means, I will explain then in the second half of the presentation, when we will automatically generate code out of this model that will later run on the microcontroller. Shortly, they will just, let's say, they will help you to configure the different peripherals this microcontroller offers. So for example, here this PWM block will configure the PWM module on this microcontroller. Then here we have the actual control algorithm. So we have inner voltage and current control loops. And here this outer current control loop receives its reference from two different sources depending on the state of the DC microgrid. In normal operation, it receives the current reference from a droop controller. The droop controller will control the DC link voltage towards the reference value, and will also enable to have load sharing among different systems that operate in parallel. So here the droop controller is quite simple. So we provide a voltage reference, compare it against the voltage measurement, and in the end, after multiplying with a certain droop gain, directly here the current reference will result in order to stabilize the DC link voltage. You will see then later in the simulation results that at simulation start our DC link is fully de-energized. So we need some kind of startup sequence in order to build up the DC link voltage. And this is also then achieved, or this is implemented here with a simple state machine. And when we start up our DC microgrid, we'll just use here a constant current to build up the DC link voltage in a smooth way. And when we overpass a certain threshold voltage, we switch then to just the control mode. So this is the controls for the two battery storage systems. The Grid Interface Converter has also its own controller that will then later run also on a microcontroller. Also here you can then therefore identify those target-specific blocks that I will explain later. Let's focus now on the control algorithm itself. Here we have quite a traditional way to control this three-level NPC converter. So we have an inner current controller on the D and Q axis. The D current controller receives its reference value at the moment here from an outer power control loop. So here in this measurement transformation block, we can calculate the active power, and we can compare this then against the reference value. In this simulation run, this reference value is just a fixed value, but later, or let's say in a real implementation, some kind of supervisory controller will provide this power reference in order to, let's say, to fulfill the requirements from the distribution system operator, or in order to exchange then a certain amount of power with the DC microgrid towards the mains utility grid. So this is the simulate or the controls model that we use for the grid interface converter. And let's analyze now the simulation results that we get for this scenario. Actually, what you see here on the schematic level, you can see that the PV production and the concept power load receives a power reference that is provided here with a one-dimensional lookup table. So in our case, this is some real measurements that were taken on a PV array, a certain load cycle, and this will then just produce some power flow variations in our microgrid. And here are the simulation results. If I zoom a little bit out, you can see at simulation start, our DC microgrid is fully de-energized. We start to build up the DC link voltage in a smooth way. After a certain voltage threshold is passed, we switch the control mode to the droop control approach. And actually, you can see here for all different operating points or operation conditions, the DC link voltage stays close to the reference value of 750 volts. This little deviation from the reference value is standard or is normal for this droop control approach. This is because we have no integral action in our controller, in our voltage controller, so there remains a certain voltage deviation that is then proportional to the power output of the converter system. But you can see here this deviation is in the range of plus minus 2 volts, so this is acceptable. Here in the second plot you see the different power flows, so the power output of each conversion system. First of all, here in green, the power output of the PV production array, or of the PV production. You can see you can test and fast changing power outputs due to probably some shading effects. So you can, here in simulation, you can simulate all different operation conditions. In blue, there is the load, so the amount of power that is consumed by this constant power load. In red, we have the power that is exchanged with the mains utility grid, so with the AC grid. You can see during normal operation here, our grid interface converter exchanges the 5000 watts that are set in the control loop. Here in yellow and in Violet, you see the balancing power that is provided by the two battery storage systems in order to stabilize or to operate the DC link, the DC microgrid. They need, in fact, to equilibrate here the power to 0. And you can see that the power sharing is not ideal, so it's not identical. There is a little difference here in the power output of the two conversion systems. And in fact, this is due to different line impedances. So each conversion system, if we open again here our schematic, is coupled over some line impedance to the common DC link feeder. And here, these line impedances are different, especially here for the line resistance that is that will define the steady state behavior. And this, in fact, will then generate here this mismatch in the power output. So the load sharing is not ideal. There are some techniques to balance this mismatch or to resolve this mismatch, but here no such technique is used. In the third plot here, you can see the AC grid voltage. We can see that here at t equal to 0.5, the grid voltage, the AC grid voltage sags down to 0 and remains there for until t equal to 0.8, where the normal grid operation is restored. You can then see the effect or the behavior of our grid interface converter. So here at t equal to 0.4, the enable is given, so we start to inject our power of 5000 watts. When we detect here this voltage sag, the operation is stopped immediately. After the grid voltage reoccurs, we have a short synchronization phase, and then we start again to inject the demanded power with the mains utility grid. So here, already in offline simulation, enables you to test different scenarios, to test different operation conditions for your control approach that you use. You can use this then also to design here the different converter systems to see if all currents and voltages remain in this in the nominal conditions of the power MOSFETs that you tried, that you intend to use, and so on. So you have then here quite a flexible test bed in order to test different scenarios. Let's now make the transition between the offline simulation that I've shown you just before towards the real-time simulation running on the Rtbox. So I will introduce now this concept here on a few slides. There are some fundamental differences between an offline simulation and a real-time simulation. In an offline simulation, we have absolutely no time restrictions, so our simulation model can either run slower or faster than real-time, and this is usually not critical. We can then just use variable time step solvers in order to solve our model, and all our simulation models are implemented in continuous state space. For a real-time simulation, we have a hard requirement, so we always need to stay synchronized with real time. So that means later our simulation model will be executed with a fixed calculation period here on the real-time simulator. First of all, for this, our system model has to be implemented in discrete state space. And then we have to make sure that the computation of the system model is finished in such a discrete calculation period. If this is not the case, we cannot hold our, or we cannot respect our real-time criterion. However, you don't have to make this transition between the offline simulation and the real-time simulation manually. This is the job of the PLECS coder. So for a physical model, the PLECS coder has to do the following steps. So first of all, you still implement your models in continuous state space in PLECS. So first of all, the PLECS coder has to extract all the different state space descriptions for your model. And since we have switched models, this will result in one state space description per switching combination. Each state space description is then discretized with a certain step size, T of D. In the end, the PLECS coder will output generic C code that fully describes your physical model. However, this is then just generic C code. Everything that is target related is provided by us in a so-called target support package. So a target support package typically consists of different target blocks. So in order to address the different peripherals the target offers, the hardware target offers, there you will also find everything that is needed in order to generate automatically a runtime executable that can directly run on a hardware platform. So you need for this some platform-specific drivers in order to address the different IOs, the different peripherals. You need then for sure, let's say, a target-specific cross-compiler and so on. So all this is provided by us in a so-called target support package. At the moment, we provide target support packages not only for the Rtbox, but also for different microcontroller families. So at the moment, we have a target support package that you will see today for the C2000 family from Texas Instruments, and then also for the G4 series from STM32. And then the approach is quite simple. So we take then the generic C code that is generated by the PLECS coder. We combine it with the driver libraries, with the hardware wrappers, we cross-compile everything, and then we get directly a runtime executable that is then loaded directly out of PLECS on the different hardware targets. Here you can see the basic hardware-in-the-loop structure. So the hardware-in-the-loop simulation, as I already said, is a technique that consists of replacing here the physical system with its mathematical representation. The mathematical model is simulated in a real-time simulator where the measurements of the system, so for example in the model we measure some voltages, some currents, are then converted into real physical signals that are sent here to the analog outputs of the Rtbox. We connect then our system under test. So in a hardware-in-the-loop structure or in the hardware-in-the-loop simulation, the hardware under test is here the microcontroller. We connect then here the ADCs to the analog outs of the Rtbox. In the hardware target, we get the new samples based on the signals that are provided here by the real-time simulator. With those samples, we calculate the control algorithm, update the duty cycles, and this will result then in a new PWM signal. Here the PWM signal is then connected to the digital ins of the Rtbox. And this feedback is then quite critical because here a PWM signal is a fast varying digital signal. And all the information of the PWM signal is stored in the relative on and the relative off time. So we have to make sure that we can recreate here the relative on and off time as close as possible. And for this, we use some oversampling of the digital ins. Actually, we are sampling the digital ins of the Rtbox with a time resolution of 6.6 nanoseconds. This updated PWM information is then used to drive or to recalculate the simulation model, to update the position of the different switches, and then to send back again the updated measurements. The goal of this approach is really then to test here the implementation of the controls against this emulated hardware target. At the heart of the Rtbox operates a Xilinx Sync system on chip that consists here of an FPGA and multiple CPU cores. The tight integration between the FPGA and the CPU allows for low latency, for low latencies when moving data between here the I/O channel, so from the physical ports to the simulation model running here on the CPU. In the end, for Rtbox 1 we have 2 CPU cores, and for the Rtbox 2 and 3 we have 4 CPU cores. However, always one CPU core is used to run an embedded Linux in order to make the communication with the host computer and some additional services. And all the remaining cores are then used for the real-time simulation of the model. For larger systems, several Rtboxes can be interconnected together. This interconnection is done via a high-speed serial communication link that is here placed at the back panel of the Rtbox. The Rtbox has several such high-speed bidirectional links, and each of them supports a data rate of several gigabits per second. The connected Rtboxes can then operate either synchronized together or also in asynchronous mode. You will see that we will use this technique, this interconnection, and also for our DC microgrid simulation model, where we will interconnect here the Rtbox 3 with the Rtbox 1 over so-called SFP port. For larger systems, a key optimization approach is to split the complete model into 2 or several parts. These parts are described by smaller independent state-space models that can be calculated and updated then individually. This model splitting technique reduces the total number of switching combinations that need to be analyzed by the PLECS coder and decreases the size also of the state space matrices. So we will use then also this model splitting technique for our DC microgrid model. You can see here how the DC microgrid model that I've shown you before in the offline simulation and also on the slides is then split into several subsystems. In total, we have here 3 CPU cores on the Rtbox 3 that we can use to simulate our models, and 1 CPU core in the Rtbox 1. And in fact, we can then split the model as shown here. So on Rtbox 1, we will simulate one of the battery storage systems. On the Rtbox 3, we run here the Grid Interface Converter on 1 core. Then we run the second battery storage system on the second core, and the PV production and the load and also the passive structure of the DC microgrid will run on the third core of the Rtbox 3. So here's again the simulation model that we used before for the offline simulation part. So I will make now the transition between this offline simulation towards the real-time simulation and explain you a few things. So first of all, why everything is regrouped in different subsystems, then how internally calculated voltages and currents are transformed into real physical systems that can be measured in here on the analog outs, so how this has to be configured, and how the model is split into the different parts that you can see here in this graphic. So let's start here with those 5 subsystems that you see here on the root schematic level of the simulation model. Actually, here on my desk you can see 5 different hardware targets, so 2 Rtboxes and 3 different microcontrollers that are connected to the front panel of the RT boxes. And here you can see then the counterpart. So actually the model was built up in such a way that each subsystem that you see here represents the part of the model that will later run on an individual hardware target. So for example, everything that is included here in this Rtbox 1 subsystem, so the model of a battery storage system, will then later be executed in real time here on the Rtbox. And the same thing is then true for the remaining 4 subsystems. A good point or another advantage of this representation is that you can already identify here on this root schematic level which information is exchanged between the different hardware targets. So for example, you can see that here on the Rtbox 1 we have connected physically a microcontroller. So the microcontroller will then execute here the controller of this battery storage system that is emulated by the Rtbox 1. You can see that we need to provide different voltage and current measurements to the ADC of this microcontroller. The microcontroller will then send back new PWM signals that are connected to the digital ins of the Rtbox. And so you can easily identify the flow of information between the different hardware targets. You can then, for example, also see that between Rtbox 3 and Rtbox 1, the information is exchanged via this SFP communication link. So this low latency interconnection possibility to interconnect different Rtboxes together. You can then also see that there is no communication between the different controllers. So that also means that we just have here some local control, this local control approach implemented, so the droop controller. So let's explain now how this information is then physically also be made available here at the front panel of the Rtbox. For this, let's open here the Rtbox 3 subsystem and analyze a little bit this part here of the model. So here we analyze how the Rtbox 3 interacts with the Grid Interface Controller, or the controller of the Grid Interface Converter. So you can see here that we, for example, we measure the current that is flowing towards the mains, we measure the grid voltage and some values on the DC side. So this information has to be made available also physically here at the analog outs of the Rtbox. And this is done by using so-called target blocks. I've explained you before that in order to make the code generation process target specific, we provide a so-called target support package. One part of this target support package is the target specific library. And this target specific library that can be included then in the normal PLECS library browser contains different blocks in order to configure the peripherals of the hardware target. So let's open here quickly the library browser. And here you can see this new entry, PLECS Rtbox, that appears in my library browser because I have installed the target support package for this hardware target. And in there you can find different blocks in order to configure the peripherals that the Rtbox offers. So for example here a block for the analog output signals, digital ins, digital outs and so on. Then also, let's say, some advanced blocks in order to use some communication peripherals or communication interfaces the Rtbox provides and so on. So here in our simulation model, for example, we measure the grid current in our simulation model. This information is then made available to the microcontroller by using an analog out block. So here we can then say on which channel we want to output this, what's the scaling and the offset in order to make the voltage range that the Rtbox outputs compatible with the voltage range of the microcontroller. So usually a voltage between 0 and 3.3 volts. And yeah, that's how the information that is calculated internally in the simulation model is then made available to an external target or to the external world. In order to read back the PWM signals that are provided by the microcontroller, we use a so-called Pwm Capture block, which will then automatically generate the gate signals for our converter. And so those target blocks are then used to make or to configure the different peripherals of the Rtbox. As you will see later, we will not only generate code for the Rtbox, but we will also automatically generate for the microcontroller targets. And also to do so, to create target-specific code, also there we need a target support package. And in fact, there is also a target support package for TI that we offer, and we use the blocks from this TI C2000 target library in order to configure the peripherals of the microcontrollers. So let's open here the battery storage system controller. Here you can see the target blocks with the small annotation TI that I've already shown you in the first half of the presentation. So here you can see, for example, with this target block we can configure the PWM module that this microcontroller offers. So here you can see that we can configure how many PWM signals we want to generate, what's the carrier type, the carrier frequency, the blanking time, and so on. So here we can configure the peripherals from a high-level point of view. So we don't have to configure or to set all the bits in different registers by hand and by scanning through thousands of pages that the user manual of this microcontroller has. The next point that is open is to explain how the model, the complete system model, can be split in individual subsystems. So for example here, in this graphic you see that on the Rtbox 3, which offers 3 CPU cores that we can use to build our models on, is split into 3 different parts. So one CPU will simulate or emulate the behavior of the Grid Interface Converter part. One core will run the model of the battery storage system, and one core will run here the passive structure of the microgrid together with the PV production and the load. So let's see how this is implemented in PLECS, or how this model splitting can be implemented in PLECS. So in fact here for the battery storage system, you can see here this coupling circuit. And that's exactly the way how a model can be split in individual parts. So let's open what is included in this, or what is hidden in this coupling circuit subsystem. Actually, what we do here is the following. So here the converter system has capacitive behavior at his output. So here we have a coupling capacitor. The voltage over this capacitor is assumed to change just slowly from one time step to another. So we can measure then this voltage here by using just a normal voltmeter, provide this information to the second coupling circuit, and here on the DC link side we can impose then this voltage, this measured voltage over this capacitor, by using a controlled voltage source. The other way around, we can do exactly the same thing. So here on the DC link side we have inductive behavior. So we can measure the current that is flowing through this inductor by using the ampermeter, providing this information then here to the other coupling circuit, and impose the current here on the converter side. And that's how the information is exchanged between the CPU or the model here, the battery storage system that runs on another CPU, then here the DC link part. For information exchange between the Rtbox 3 and Rtbox 1, the approach is exactly the same. The only difference is that we cannot directly pass the information here, or we cannot pass the information directly, but we have to connect it, or we have to pass the information over this SFP communication link that the Rtbox offers to create a low communication, low latency communication between different Rtboxes. So let's open this part. So here on the Rtbox 3, we will just run one half of the coupling circuit. So the half that is connected here to the DC microgrid structure. So here we measure the current flowing through this inductor with an ampermeter. Or with this ampermeter, provide this information, and then we get from the other Rtbox the voltage that is measured over the output capacitor. You can see here that here the measured currents that are flowing through this inductance are called I_BSS2, and this I_BSS2 is then sent here over SFP to the Rtbox 3. So here we use an SFP out block from the target library of the Rtbox. We receive then the information about the measured voltage over the capacitor of the second battery storage system by using an SFP in block, and we can then just inject here the signal on the DC bus side. So if we open here the Rtbox 1 model, we will see then here the second half of the coupling circuit related to the converter side. And that's how a model is split then between different Rtboxes by using this SFP communication link. So let's initiate now the code generation process. For this, I open here the coder options. The first thing that we see here is that we can identify the 5 subsystems that we have here on root schematic level, also here in this list. And that's then the key way to tell the PLECS coder on which hardware target you want to generate code for each subsystem. So for example, later we will then say here PLECS Rtbox 3 subsystem will run here on a PLECS Rtbox 3 target. But let's start here with the Rtbox 1. First, I will have to toggle on or to switch on the Rtbox. In order to pass the information or to exchange the information between the Rtbox 3 and the Rtbox 1 and vice versa, I have to interconnect them together over the SFP ports. I can do that with a so-called SFP cable and then just connect it here to the back panel SFP ports. So this is done now. Now we can start to generate code. First for the Rtbox 1, then for the Rtbox 3, and in the end for the microcontrollers. I will start here with the Rtbox 1. So this time the target is a PLECS Rtbox 1, and I can search for an available Rtbox in my local network. When I click here on Build, the PLECS coder will first discretize this model, generate generic C code out of it, cross-compile it for the target Rtbox, and upload it to the box. And as you can see, that this build process is already finished. Now let's do the same thing for the PLECS Rtbox 3. Also here I can search for an available box in my network, click on Select, and then also initiate the code generation by clicking on Build. Also this time this build process is finished quite fast. If you focus here on this view, you can see now on this little display that the model is now executed in real time on the Rtbox 3 and indicated with this blue LED also on the Rtbox 1. So the next step that we have to do is to generate code for the microcontrollers. I will start here with the microcontroller that is connected to the Rtbox 1. Here in the coder options, this time it's not an Rtbox, but it's an TI 28069 target. So a Piccolo launchpad offered by Texas Instruments. So I just choose the right target, and then I can build the control code here out of PLECS. So this time the PLECS coder will generate generic C code here for the controller subsystem, cross-compile it for this microcontroller target, and directly flush the microcontroller out of PLECS. So in the end, what you have is a one-click solution in order to generate a runtime executable for this hardware target family. And this is done. Actually, for the other two microcontrollers, I already pre-flashed them before in order to save some time. So at the moment, this real-time simulation is executed in real time as well as on the RT boxes, as well as here on the 3 microcontrollers. So at the moment we lack a little bit of feedback, so what's happening, what is calculated, for example, inside the boxes, and also what's happening in the microcontrollers. In order to get some feedback, we can connect the so-called external mode between our host computer to the different hardware targets. So I will start here with the Rtbox 3 and connect external mode. Can activate here the auto triggering, and let's open now the scope here. So here in this scope we have now a live view what's happening on the Rtbox 3. So we can see here the grid voltage. We see that there is no power flow at the moment happening in our microgrid, and that the DC link voltage is at 0. So our DC bus is fully de-energized. Actually, I configured here those dip switches that you see here on this view in order to give an enable for this battery storage system controller. So if I toggle here the 2 switches, the DC link startup phase will be initiated. So let's do that. You can see now here in the scope that actually this battery storage system controller controls the DC link voltage close to the reference value of 750 volts. At the moment there is not much going on in our microgrid. So let's switch on also some production and some loads. For this I go back here to the PLECS schematic, and I can now interact with the model that runs on the Rtbox, also the other way around. So I can also send the new data to the Rtbox. For the moment I will just toggle here those 2 switches. And what you see now is that the PV production and the load is activated. So we have now some power variation happening on our microgrid. We can then also see that the single battery storage system that is running now maintains the DC link voltage close to the reference value. So let's switch on also the other battery storage system in order to test the parallel or the load sharing between the 2 systems. So also there I can toggle the dip switches, and you can see now that here the yellow and the violet curve, is the power output of the 2 battery storage systems, that they maintain the DC link voltage in parallel operation. Let's switch on also the Grid Interface Converter. So also there I configured some dip switches in order to give the enable of the Grid Interface Converter. And now you can see that our Grid Interface Converter is exchanging 5 kilowatts between the DC microgrid towards the mains utility grid. What we can do now is to connect this external mode not only to the RT boxes but also to one of the microcontrollers. So I will again open the coder options and connect external mode to the Grid Interface Converter controller. So also there I can click on connect and activate the auto triggering. I will open now here this controller subsystem in order to change some set points. So as you can see now, at the moment we exchange 5 kilowatts between our DC microgrid towards the mains utility grid. Let's change this set point a little bit. So I can change now on the fly in real time the reference value from, for example, from 5 to 2 kilowatts. If I click here on apply, I will send the new set point to the microcontroller, and you can see the immediate change here in the power output. And if I change it then back to 5, you see the reaction here. So you can not only, with this external mode, you can not only read information, but you can also then set new information in order to test different operation conditions, to change configurations and so on. What we can do now is also, let's say, to test how our system reacts if we lose one battery storage system that controls this DC link voltage. So also there, I can then just toggle again here the dip switches, so to make this system trip. And you can then see that actually here the power output of this single or of this battery storage system 2 is going to 0, but the microgrid remains stable and we are still able to operate it. So now the DC link voltage is controlled by a single battery storage system. So in the end, what you now have is a really cool testbed that can be extended quite easily by just connecting more and more boxes together. If you want to connect additional loads and storage systems and so on. Over SFP, you can then connect new boxes in a modular way to your system and to make your DC microgrid larger and larger. So let's go back to the slides in order to make a short summary of what we have seen in this presentation. First, I gave you a quick introduction to some fundamental microgrid concepts and also some challenges regarding the simulation of them. You should have now a clear image how you can use the PLECS tools for your microgrid development, so for offline simulation and also for real-time simulation. The value of real-time simulation regarding microgrid projects is quite high because you can test the control approach that you have in mind in a safe environment without having the need to have a physical prototype available. And especially in microgrids where you have not only a single system to test, but an interconnection of multiple systems, there you can have a clear benefit if you test your controller in real time. Then we have seen a little bit the transition between an offline model and a real-time model and what has to be done in order to do so. So thank you for joining this presentation, and if you have any questions, do not hesitate to reach out to us and to write an email to info@plexim.com.